Then I'll show the processing of 2D NMR. What I'll do is I will just open the actual software and I will demonstrate that how to do a processing of the 2D experiment in delta sets. Okay, let's begin. IIT Patna is having ECZ 500R system. It's basically a 500 megahertz NMR, and it has both the capabilities, solution state NMR and solid state NMR both. In solution state case, you are having the one of the highly advanced probe that is called the Royal HFX probe, where you can do a proton fluorine decoupling. Plus, the interesting fact about this probe is you can do experiment with the X. X is basically a broadband. You can do X nuclear, like a carbon with the fluorine and proton simultaneous decoupling is possible to do that. Or any X, like a phosphorus, silicons, or selenium, borons, aluminium, with the decoupling of the fluorine protons is possible simultaneously with this probe. And of course, there are routine 2D experiments, those also possible system. In solid state case, you have HX mass solid state probe. You can do a CP mass experiment for the different nuclei from phosphorus to nitrogen. You can do that. And software is a Delta 5 E5. And this is basically acquisition software, but there are currently free versions of Delta. Higher latest softwares are available. You can download that for your data processing sites. Highlights about the instrument is you can do all the routine 2D experiment, 1D and 2D NMR, both you can do that. The nuclear you can do from proton and the fluorine plus phosphorus to nitrogen. It's completely a broadband range. Just to name few, you can do boron, aluminium, silicon, selenium, platinum, tellurium, lead, lithium, sodium. These experiments is possible to do with your system. Plus special experiment like a NODI experiment, non-deuterated NMR, you can do it. QNMR, kinetic experiment. Kinetics basically a time-dependent experiment, concentration-dependent experiment, or you can say that is a different parameter if you want to vary, and you can check the experiment, you can do that here. And all 1D, 2D experiment like proton, fluorine, phosphorus, nitrogen. And this is a specialized experiment, I mentioned that. And some of the few new experiments like a DOSY NMR, water suppression experiment, water log Z. Water suppression is basically, suppose you have a huge water signal in your sample spectra, and if you want to suppress the peak, you can suppress your water signal from your spectra. You can do that. Water log Z is something like that STD kind of experiment, is saturation transfer difference experiments, or you can say protein ligand bindings, which is mediated by the waters. You can hit the waters, and if it is a ligand is binded to a proteins, that will be interacted, and you can give the signal in the water log Z experiment. And CPMGs, again, it's a kind of filtering experiment, or you can use it for T2 measurement also. CPMGs, if you have a sample with a big molecule like a protein plus smaller molecule like a ligands are present, and when you record a proton NMR, the peak becomes very broad. That's because of the protein signal. And now in that, there are ligand signals are present. And if you want to see only ligand signal, you don't want to see any kind of protein signal in the sample, you can filter out your bigger molecular peak from the CPMG sequence. Out your protein peaks, and you can pick up only your ligand peaks. T1, T2 experiments are relaxation measurement experiment. It's a very good experiment for identifying the dynamics of the molecule. You can do that. HSQMB is one of the new experiments. It's basically not a new experiment. Experiment is a very old one, but it was highly optimized in our system. Now you can use this where you can do the heteronuclear J coupling values can be identified. J resolved HMBC, H2BC experiment. There are many big list. You can use those. Variable temperatures in solution state -100 to +150 degree, you can do it. So, and if you have any special requirement of the experiment, please let me know that. I can give you my email ID, and you can just say to me that if you want to do that, I can check the possibility which is possible. Then I'll let you know that those can do it in your system. And let me begin to the 2D NMR data analysis side. See, the first questions comes, why require 2D NMR? That's called why multi-dimensional experiment is required. In 1D NMR, all information is present. Okay, information basically exists in the 1D NMR. It's like all the interactions are present. But the problem is, if it is a very small molecule, peaks are well resolved. You can easily make assignment of the peak. and easy. But what about if molecular size is big and proteins or polymers kind of big? Spectra looks like this. Such a huge complex spectra, it's very difficult to extract the information out of from this. For to extract the information buried under these peaks, that we require a multidimensional experiment. So what we do is the information we are spreading from 1D to a 2-dimension, second dimension spreading that. If still this complexity is there in the 2D NMR, we can spread this information third dimensional. It's called 3D experiments. Okay. So we have to choose the one specific information and extract it in the Y scales. Just an example. So in this might be having chemical shift and the coupling constant both. And even it has an NOE, relaxation effect, dipolar coupling, quadrupolar coupling, everything is present. But just to name a few things, one is chemical shift and the coupling values. Now using 2D experiment, you can spread the chemical shift here and coupling constant in the direct, indirect dimension. So that is kind of called the 2D experimental sites. So to reduce the complexity of 1D spectra, we require the high dimensional experiments. So that. In NMR cases, the major parameters obtained are one is chemical shift. It's basically a frequency scale, spin-spin coupling, and that's we call it is the J values, and intensity of a signals where you can do the integration of the peak, right? You can do that. And relaxation, NOE, dipolar coupling, and the quadrupolar couplings. This is we generally see in the very weak dipolar coupling in the solution state because molecules are completely motion or transition motion is present. So that is vanished. And quadrupolar coupling is present only if your molecule having the quadrupolar nuclei, like a boron or aluminum kind of things. And this is majorly dominated in the solid state in the condensed matters. You can see that. So in 1D experiment means you have one chemical shift and second dimension is intensity scales. Your chemical shift or a frequency scale is indicates dimensionality. Now in one chemical shift, 1D NMR. And if you have a two chemical shift number 1 here, 1 in this place, this is called a 2D experiment. Okay. So you can make your own 2D based on your interest in things. Now example, so if you make a proton to proton, you can make a proton to proton 2D experiment. That's a well-known experiment. We all know that. That's called the COSY experiment. And you can spread carbon chemical shift on the direct dimensional, and in the indirect dimension, you can spread the proton chemical shift. That is called the head core experiment. And if you talk about a proton side, it's called the universally detection one that we have experiment called HSQC experiment or HMQC experiments are called that's also heteronuclear experiment. We can make our own design of experiment based on the nuclei or based on the parameters also. So 2D NMR is like this, the two chemical shift, frequency scale 1 and frequency scale 2. And there is one more scale, that's a common scale, that's called intensity scale. Okay, actually it's just an intensity, there's no much information. Information is spread by the frequency one. In generally what we see is we look at in the contours view. So in the top view, we're looking that. So this signal looks like a contours like this. Okay, so that's why 2D contour plots, this is called. Now, I just want to go in a little bit more about the 2D experimental side. If you see 2D, this is just a representation of 1D and 2D NMR. In 1D experiment, in generally, we have a two-part. The one is called the preparation side. Another one is the detection side. Okay. Preparation side may be a relaxation and the pulse both. In 1D proton or carbon experiment, we'll be having the one relaxation delay and one transmitter pulse. After the pulse, the coil starts receiving a signal that's considered as FIDs. So we will convert that FID into a frequency scale. We'll get an NMR spectra. So there is no separation. If peaks, chemical shift or chemical environment is almost matching, then peaks get merged just like this. So to resolve, we can spread into a two-dimensional. In 2D NMR, we have 4 parts. One is called the preparation side. At the beginning, as I mentioned, 1D. Same second is evolution, where you will be having the T1 relax or T1 delay time delay, then the mixing time and the detection part. Now this is called a dimension, T1 dimension, T2 dimension. T1 dimension is basically indirect dimensional and T2 dimension is a direct dimensional. Now it's the 1D experiment one where the peak is merging over here. In 2D experiment, you can see the diagonal peak is still merging, but if you have a correlation, you can see a cross peaks in the spread it into the two-dimensional view. Okay, this is how you can use that. So just some from the basic 2DX sequences are So as I mentioned, the 4 part: preparation side, evolution, mixing, and detection part. So just representation here, you can say pulse and delay, then the delay here. Now this T2 may be a delay or maybe a pulse. And even the mixing time also may be a delay or the pulse. Just an example, in the case of cozy NMR, you have one pulse at the beginning. This is considered as a preparation pulse. Okay. Then we have a T1 delay where there is a, based on the J couplings, there is a mixing up of the magnetization and it transfers via the J coupling values. Now, after that, there is a pulse. This is pulse is called, we're transferring the whatever the information present in the T1 into the direct dimensional. So that's why it's a preparation or mixing time. In toxic case, T1 is same, but mixing time will be having the spin lock. Instead of a single 90-degree pulse, we are having the spin locking pulse, where it's kind of the decoupling, or you can say that the magnetization transferring locking pulses. So during this period, what happens is the magnetization will transfer from 3 bond to a 4th, 5th, 6th bond, wherever the till J coupling proceeds. Till that point, the magnetization transfers.
And Dr. Nivash,
Yes,
here
ma'am.
I have a question. In 2D experiment, in all experiment, spin will be off, or in some experiment, spin will work?
Ideally speaking, you can turn it off the spin for all the 2D experiment. But in the some of the basic experiment like a cozy or HMK's experiment, if you spin it on also, it won't make much difference. So because
Okay.
these are magnitude mode experiment, it's a very strong
Yeah.
experiment. It can suppress those spinning sidebands and issues. So
Okay. So that's
answer
why
is
spinning
for
is off, no?
yes. In 2D
Oh,
experiment, you should spin off all the
okay.
experiment.
Okay. Okay. Thank you.
And in a nosy experiment, so here mixing time will be like just a delay and the pulses. And during these cases will be the your magnetization transfer that.
Acha, one more question I should ask previously. Hello.
Yes, ma'am. Yes, ma'am.
Actually, I should not ask, but our customer asking, nosy experiment in broker and nosy experiment in this machine, geol machine. I think
Hmm.
both are different, or it is taking so much time, but there it takes less time. So, what is behind that?
It depends on the number of scans and the T2 increment, ma'am. Here in the experiment, you can see that T1 increment and the
Okay,
number of scan repetition of this experiment.
okay,
Now, if you keep a same T1 increment as the Brooker system, the user using that, and
hmm.
same number of scan repetition time, if you use that, the experiment time becomes exactly same. In generally,
Hmm.
so whatever the template we have created in your system, that is based on
Okay,
the generalized template. We have used a more
okay,
number of
okay,
scans and more
okay.
T1 increment.
Okay, okay.
That's
So
why
right
experiment time is
now
more.
it will be possible to create a new template for running nosy experiment.
We can do that. It's not the problem. We can do that. And
Okay,
even I
okay.
can teach you. It's very simple. That is called the,
Okay,
in
okay.
our
Okay,
terminology,
okay.
Y scale T1.
Okay, I will talk you later.
Yeah.
Okay.
Yeah,
Thank
I
you.
can create this. So this mixing in that nosy as in the toxic experiment, spin lock is very important. Based on how much long you keep the spin lock on, that much of transfer will happens for the magnetization. But in the case of nosy experiment, the mixing time is important. During the mixing time, what will happen is your magnetization transfers via dipolar couplings. It goes to through space couplings part. Now that again depends on the molecular dynamics also. So these are the important factors. Maybe we can discuss during the specific experiment discussion time. So here just I want to show that the representation how 2D will be taken care. I mean 2D will be done in the instrument side. So I have taken an example of cozy experiment. You have a two pulse cozy I mentioned, preparation pulse and the final one is mixing pulse cases. Now the first point during the first T1, the gap is very, very small. We will keep the T1 maybe 0 seconds. Apply pulse, immediately apply the pulse and get the FID files, free induction decay. Then we'll increase the gradually increasing T1 values, maybe T1 plus delta T1. Then we'll again acquire the TD FID. Similarly, we'll keep on gradually increasing T1 values. So ultimately, we'll get a number of FID files like this. Plus, we are getting the number of T1 values, T11, T12, T13, T14 like this. We'll get a number of points. If we increase number of points more and more, experiment times more and more here. And how it will be constructed in 2D ways. These are the FID files we are collected in the direct dimensions. Okay, so we'll be like this. Hello, ma'am, I'm audible, right?
You are audible.
Yeah, because my internet something unstable. It's being lost. That's
No,
why.
but
Okay.
continuously you are audible.
Okay. These kind of FIDs. Now, generally, what we do in the 2D NMR, these collected FID will collect and place it in one of the storage place. Then after this FID, we'll convert into a spectra and just make a Fourier transformation. The first FID here, there is no delay. So there is no phase distortion here. So you will get a proper signal like this. And when keep on increasing the delay, there is a distortion in the phase like this. It's keep on distorting like this. Okay. Now the direct dimension Fourier transformation done. Then if you look from the indirect dimension, this also looks like a FID. And this FID, if you convert, this is called direct dimension Fourier transformation, and this one is called the indirect dimension Fourier transformation. Then you make that Fourier transformation, will get the contours. Now this phase distortion is depends on the delay, and delay again depends on the J values, coupling values. Now, if you have a coupling constant, coupling between the signals, then you will get a cross peaks for this. So this is how 2D NMR will be collected methods, but the contours depends on the delay, how much we're using in between that two. And again, not only delay, there is in the NOSI experiment, if I have a mixing time, that depends on mixing time also. Now, in case of, okay, this is a brief introduction of a 2D experiment. I just want to go further. So 2D NMR can be classified, broadly classified into three categories. The one is resolution suppression experiment. Second one is correlation experiment. Third one is called the multi-quantum experiment sites. In most of the chemists or the routine experiment, we are using only this category of experiment, correlation experiment, not the resolution, not the multiple quantum. What is the resolution experiment? See, in one dimension, I mentioned that there are so many parameters that are present. Like you have a chemical shift, Zeeman effect, you have a coupling constant, you have dipolar couplings, you have quadrupolar couplings, NOE, relaxation, everything is merged over here. But resolution experiment means separating these two parameters called the resolutions. In this category, this experiment, one, the direct dimension will use only single peak for individual frequency, chemical shift. But indirect dimension, you can see only splitting patterns, multiplicities. This is one of the very well-known experiment. It's called 2D J-resolved experiment. You can resolve your coupling values. This is kind of the resolution. It's not only a J-resolved. We can design for a different nuclei also. And another experiment, multiple quantum experiment, is like when you make an NMR, in an NMR samples, there are so many signals that are present, sample spins are present. And when you consider single spins, that's called a single quantum spins. And but in case of samples, it's not like this. All are coupled each other. So this is becomes called the multiple quantums. Okay. When the two spins are coupled, the frequency of the two spins are resultant will be different. So to extracting that information is called the multiple quantum. So, and this kind of information cannot be done with the direct dimension. It has to go to indirect dimensional sites. So that will be indicated in indirect dimensions. And this kind of experiment is very useful for when you have a multiple ring systems in your case, like you have uh, quinolines or anthracines, or you can 2 rings, 3 ring systems. If you want to separate in NMR signals, then these multiple quantum experiments are very useful in the categories. But it's not much research working on these sites. The only methodology development we have done a couple of things in the, you can see the papers. Now, the very famous in NMR is called correlation experiments. We have many correlation experiments, but in routinely, in generally, we have only few experiments we're using for the chemist. I can classify that 2 experiments in 2 categories. One is homonuclear correlation experiment. The second one is heteronuclear correlation experiment. Homonuclear experiments are J-resolved, COSY, TOXY, NOSY, ROSY. These are between the same nuclei. And heteronuclear experiments are different nuclei, HMQC, HSQC, HMBC experiment side. So if you want to use NMR spectroscopy or structural elucidation site, here is some of the basic experiment stuffs we are generally used for structural elucidation. The one is 1D proton NMR, where we'll make the count of the number of the protons here, chemical shift. You can see each chemical shift frequency give different peaks for you. And carbon NMR, that number of carbon, counting number of carbon gives a number of peaks. Peaks indicates the different chemical environment carbons. Depth experiment, again, it gives two different groups, CH group, CH group, CH groups, and quaternary carbons are not visible in the case of depth experiment. So cozy experiment gives a proton-proton connectivity experiment. Like you have a molecule like this, where you have a proton coupled with the 1 bond, 2 bond, 3 bond, and again 1, 2, 3, fourth bond. Now, when you have a 3 bond connectivity through J couplings, you can get the information in the cozy experiment like these two. And toxic experiment is a relayed cozy. It goes to not only 3 bond, it can go to further bond, like from this proton to this proton. This is away from how many bonds? 1, 2, 3, fourth bond away. So these couplings also can be seen in the toxic experiment. HSQC, head core, HMQC, all these three experiments use the same information. There is a one bond correlations, like in this case here. So you have this proton is coupled with this carbon. So these informations can be seen in the HSQC, head core, and HMQC. All gives the same information. HMBC is basically a heteronuclear multiple bond correlation experiment. It's a long range connectivities from this proton to a long range coupling. Like this I showed here, only this 13C, this is not NMR active. And if your chain is continued, you can say that proton gives coupling for the next carbons also. That information can be obtained from the HMBC. And nosy rosy are the stereochemistry part. This is the final step of structural elucidation. So to find out the 3D structure of the molecule through space coupling can be obtained from the nosy and the rosy part. Let me go in detail one by one experimental side. Now let me go the basic experiment, cozy experiment. The cozy is the first developed 2D experiment. Okay, so when the 2D publication came and this is the experiment was demonstrated. And here the correlation between the homonuclear, like example, proton to proton correlation can be obtained. And it's not only for a proton, you can make it for the carbon to carbon or phosphorus to phosphorus. But in case of carbon on carbon, there is a different experiment name is given. That is called inadequate experiment. Inadequate or the adequate experiments are there. That's also kind of cozy experiment, but that's specific for the carbon case. And in the cozy experiment, correlates the proton resonance coupled through 2 or 3 bonds away. It's not more than that. Like here, it's like you can have vicinal coupling, or maybe you can this proton may be coupled to this proton. You can see in the cozy experiment. So the plot looks like this. The direct dimension proton plot. So in regular operation set, you have to load the high resolution proton spectra here. And this is a contour plot. And this indirect dimensional proton spectra has been plotted. And this diagonal peaks having no information. Only the cross peak will be having the information. Wherever you can see the cross peak between the diagonal peak, it indicates means these two groups are connected. Maybe you can see 3 bond away, or maybe it's maybe the fourth. It's connected each other through couplings. It can be seen. We take an example here. So okay. So here it's a self-correlate experiment 1. You can have examples of you have geminal couplings or vicinal couplings or this fourth bond couplings, or if you have allylic kind of connectivities also can be seen here. Now, this is geminal coupling will have a very strong coupling constant, couplings, 2 bond coupling, right? You may be contour size may be very strong over here. Vicinal is slightly smaller, and maybe fourth bond even weaker, and diagonal peaks is of course it's a frequency, it's a direct peaks from the individual group. And please remember that in the cozy experiment, diagonal peaks not having any kind of information. It is same like a 1D proton experiment. Okay, the information is only is a cross peak. Let me give you some of the example set up here. Okay, in this category is just a representative 2D experiment data. Now you can see you have a molecule where you have 3 spin systems, spin CH3 methyl group, CH2, and C3 here. So if you plot, you can see now this is a diagonal peak. Now this CH3 is coupled to the CH2. So you will can see there is a cross peak between the CH3 methyl and methylene. These 2 peaks diagonal, you can see a cross peaks. So this indicates the coupling partners. Let me take a real example here. So the example is I have taken ibuprofen. See if you make a numbering of the spin system. Okay, so this numbering is given based on the chemical shift. Now they completely shielded chemical shift, maybe it's near to 0 to 3 ppm CH3 peaks, and then this 3 and the 4th and then the 6th and 7th for aromatic one, and this one numbering is given. Now let's, if you want to make a spin groups, as I mentioned in the cozy experiment, cozy can transfer only from the 3 bond or maybe from the 4th bond. It cannot go further onto this. Based on that, they made a spin group. You can see H1 and H5. H1 and H5 are 3 bond away, 1, 2, 3. So you can say one spin system. Of course, this proton cannot give a coupling between this one. It's very too far, and that too there are some heteronucleus are present over here. Similarly, these H7 and H6s are coupled. And here you can see H2, H3, and H4. These are coupled. These 2, 3, 4 are coupled in systems. Now, if you record a cozy experiment for this, now you can see cozy gives one diagonal peak. Okay, no information, you can ignore that. Important, interesting is called the cross peaks. Now you see number 2 spin system, it's diagonal. Now we get a 1 cross peaks at this place. So that's a 3. So it means this is coupled to this one. Similarly, the 3 is given a correlation 2. Now next is a 4th and given to 3. This is a 4th and 3 give a cross peaks over here. You can see correlation. So this kind of useful information can be obtained from the this experiment, and this is a homonuclear one. And if you get these data, so at least you can get some of the pieces of information now, which wherever the connectivities can be seen over here. So now the 5th one. Now the 5th one here, it has given the cross peaks between the number 1 here. Okay, let me put the line here. 5th and the 1 has given the cross peaks here. So this can be seen in the cozy experiment data sets. Okay, so and it's very useful, and the most of the synthetic people, or you can see it's a fast and quick experiment. Within a 15 minutes you can finish the cozy experiment, you can get the data. So you can correlate, you can finally identify, okay, whether synthesized molecules in the right direction can be identified. The next experiment is HMQC. HMQC is basically heteronuclear multiple quantum correlation spectroscopy. It's basically a correlation between the carbon and the proton shift. Okay, and cross peaks indicates attached nuclei. Like in this example representation, proton and this carbons are coupled. This can be seen. This is a pulse program. Okay, HMQC works start with the proton magnetization, and this magnetization transfers to a carbon. This is, I mentioned X. X may be any nuclei. This is a representation of carbon. Even you can make it for other nuclei also, like a phosphorus or silicons, a nitrogen can be used. Okay, so magnetization transfers proton to a carbon or X nuclei, which is mediated by the J coupling. Okay, there must be a couplings, then it will transfers. Then the carbons or the X nuclear magnetization evolves in this T1 dimensional. Then it transfers from the carbon back to the proton. Then we are detecting the proton signal here. Okay, so how it looks like. I have again the ibuprofen sample. Now we can see there are so many proton and carbon connectivities. Now we can see we know that the first proton, this is a methyl peak. Okay, this one, and there is a carbon. There is we go cross peaks over here. Now from this you can identify that this carbon belongs to the CH3 groups. Same thing, wherever you get a peaks, that indicates the connectivity, direct connectivity part. Same HSQC also works the same manners. Okay, the working principle is different, but the ultimate result will be the same. It's also correlation between the carbon and the protons, or maybe you can say the X and the proton correlations, similar like HMQC part. The pulse program is entirely a different part. So the comparing to HMQC and HSQC little better than the HMQC wise. The reason is that in the HMQC case, during this experiment here, during this, there is no decouplings over here. This is a proton. During this period, there is a proton-proton coupling is evolved. So contour size becomes a bigger in thick in size. Okay. And if peaks are now in this case, very well separated peaks. If the peaks are merged, now contours also get mergers. It becomes very bigger in size. So HMQC is not as universal experiment. You can use it for some of the medium-sized molecules where the peaks are well separated. But in the HSQC case, it is universal, where the coupling is completely applied or decoupling bubbles is applied. So the contours are very tiny and very crystal clear. You can see that. Okay. So both are gives the same information. And HMBC, next experiment, HMBC experiment, it is again the multiple bond correlation. As I mentioned earlier, we have long range couplings. That's also picked in the HMBC case. Okay, so here you can see this can go to over the 2 or 3 bond, or sometimes it will go to 4th or 5th bond also, based on the coupling strength. Now, if you this proton after 5th bond, you have very strong couplings, maybe 10 hertz or 8 hertz. That also can be seen in the HMBC cases. Okay, so this is again, this is a pulse program of HMBC. And now, how it works out that we are applying we're taking magnetization from the protons. We're applying this pulse on the proton nuclei, then transferring this magnetization through a carbon. Then there is a delay over here. During this delay, that transfers the magnetization from proton to a further bond of the carbons. Then we are detecting this goes to the carbon, then back to the proton sides. Now, that's one interesting is there is a tau1 delay here. Filters we apply. Now, during this time, if our one bond coupling also evolves, like this direct bond, proton and the carbon direct bond coupling also evolves. So the problem is when the one bond coupling is present, the one bond and it may merges, it makes a complexity. Anyway, one bond can be seen in the HMQC or HMQC experimental side. So not required in the HMBC side. So you can filter out that one bond coupling. How to filter out that? Using this low pass filter in between. It's already inbuilt with your experiment. I think is most of our HMBC experiments, the low pass filter where the one bond coupling is removed. So, and if you want to retain that, you can just remove the low pass filter. Still, you can get the one bond coupling in your experiment sites. So I think this is one of the very useful HMBC experiment for the most of the structural elucidation cases you are using it experiment. So this is how it looks like. The indirect dimension, you will be having carbon spectra, and direct dimension, you will be having the proton spectra, and you can see the line of the peaks. Okay, so this one of the proton giving connectivity, all this, it indicates that this proton is connected to this carbon, and this proton is connected to another carbon here, another carbon. So intensity doesn't make it doesn't mean that all are in the same pattern. It may be this may be a 1 bond, this may be a 3 bond, this may be a 2 bond. There's no linearity, but of course this indicates it's the connections of the signals. Okay, so I'm just giving the brief introduction about that, and I'm not going in detail about each experiment. So you can get easily the literatures in the online. You can get those information. Okay, let me summarize the experiment which I mentioned over here. So we have many correlation experiments. In that, so the few correlation experiments are we routinely used in our day-to-day synthetic labs. So, and those are the COSY. COSY gives homonuclear short-range couplings, like a 3 bonds or maybe up to 4th bond can be seen, or even 2 bond also can be seen here. No long-range coupling, no heterolog coupling is present. Head-core experiment is basically gives a short-range coupling. Maybe you can say 1 bond coupling between the proton and the carbon. And the head core case, the carbon signal in the top of the signal, we are detecting through a carbon, not through a proton. This is basically insensitive. The sensitivity is low here because detections through a carbon, not through a proton side. Okay, it gives 1 bond. HMQC is again the 1 bond correlation, but detections through a proton side. HSQC is also 1 bond correlation. It's detection through a proton. But comparing to HMQC and HSQC, HMQC is kind of broad peak, broad contours. If peaks are merging, the contours get mergers, and then you will not able to distinguish between the peaks. So HMQC is mostly used for the medium-sized molecules, or well peaks are separated out. HSQC is kind of universal. You can use it for any type of molecule. HMBC is basically meant for long-range coupling constant measurement or long-range couplings. Still in HMBC, you can see 1 bond correlation also. And there are an experiment called, as I mentioned, low-pass filter. You can remove the 1 bond coupling from your experiment. It's possible. TOXI is basically a total correlation experiment. You can get the homonuclear correlation and long-range coupling both. You can see. Okay, these are the routine experiment. Next one is called the NOSI experiment. And I think this is also very useful for the structural elucidation of the molecule. Okay, this is the pulse sequence of NOSI experiment. And this is called a spatial correlation. So that depends on the mixing time here. Okay. So let me go to the experimental side data sets. Now, here is an example of phenylalanine. The phenylalanine, you can see that the NH over here, and you have a phenyl ring, and where the protons uh, alpha and gamma delta protons over here. And this NH protons and these delta protons are too far away from through bond if you take it from through bonds. But through space, this may be very closer by. Now, in the noisy spectrums, you will get the diagonal peak plus you will get a cross peaks. Now, if you get a cross peaks in different colors again, so between that indicates that these two diagonal peaks are spatially correlated or maybe very close by. And here, this black dot indicates a Toxi experiment. Toxi is basically a through bond, like as I mentioned, through bond couplings, like 3 bond or 4th bond can go through like this. So this is the black dot. So that's why you can see alpha protons. This proton is now coupled to the next till there is no coupling between the another protons delta here, but you can see alpha is giving the red dot. You can see the nosy peaks between the delta here. This one, you can see this. It indicates that these are spatially correlated, spatially nearby. So in the nosy works, if your spin systems are close by lesser than 5 angstrom, those peaks are picked in the nosy experiment. Okay. And the Rosie is also same. There is another experiment called the Rosie experiment. Rosie is a rotating frame over-Rauser effect. Nosy is basically a nuclear over-Rauser effect. Okay. The working principle is little different. If you see a nosy pulse sequence, you have same like a cozy type. You have a 90-degree pulse and T1 evolution time. Then again the mixing time of the 90-degree pulse. During this time, we are keeping the magnetization along the Z directions, and there is a relaxation happens. During mixing time, there is a relaxation through our dipolar couplings that will be picked as a nosy peak. But in case of the Rosie experiment one, instead of mixing time, we are applying this spin log pulse. Okay. So you can say I have given pulse sequence here only. The nosy pulse sequence gives a mixing time here, and the Rosie pulse sequence gives a spin locking one. What it will do is, so it's similar like a Toxi experiment. Once you transfer magnetization to the next spins, we are relying it. I mean, we are just proceeding further. We are just applying the power on that. So it's like the spin lock powers. It transfers magnetization from that spins to next spin system. So, but both will give the same information. Let me go into the what is the difference between these two here. So I have given the graph here where the graph indicates NOE and ROE dependence signals depending on the molecular weight. Now you see this graph indicates it's the NOE buildup, or you can see the correlation time. This is you can see the ROE or NOE buildup, and this is called the correlation time. Or you can, this is tau C is a correlation time, omega is a frequency, but maybe you can consider this is a molecular weight dependency. Now, if molecular size is increasing, keep on increasing that. So this graph looks like this is an NOE buildup curve and is the ROE buildup curve. Now you have to notice here. So if molecular weight is less, molecular size is a smaller one, you will get all the positive NOE peak. And when molecular, this indicates a molecule, you can just recorrelate into molecular weight. So if your molecular size is increasing, this NOE buildup is decreasing, keep on decreasing. One particular time, the NOE becomes completely a zero, nullified. Then if molecular sizes keep on increasing, then the NOE becomes negative. So what I want to say is, if molecular size somewhere like this, you will get a positive NOE. And if molecular size is bigger one, you get negative NOE part. But what about these areas? So here you will not get any signals. Now, in a practical situation, if molecule between lesser than 800, the falls in these areas. If molecular size between 800 to 2000, the falls in this area. So in that case, you don't see any kind of NOE peak, it becomes nullified. This is not only depends on the molecular weight, it depends on, as I mentioned, the omega. Omega is nothing but the frequency. The frequency is nothing but again the magnetic field. So it depends on magnetic field. If you change your magnetic field from 400 to 600, again this graph is decreasing. So molecule may fall in this area or this area. So sometimes you don't see a signal in the 500 megahertz NMR. Same molecule, if you take it into the 600 megahertz NMR or maybe a 400 megahertz NMR, you may see a NOE peak or nosy peaks may be better signals. That's the field dependent signals effect. Okay, that's very important. Sometimes if you say you are not getting a NOE peak or NOSI is not giving good data contours in your instrument, it's not only the issues, it may be because of field dependent part. You may see the, maybe your molecule falls in these areas. Okay, so that's why you're not able to see that.
Here I have a question. That's why we are getting not a good data for a nosy experiment here, because our some customer asking about that. Na, ki in when we are doing nosy in broker, the data is very good, and we are doing nosy here, then data
Hmm.
is very not fruitful. So
Yeah, yeah.
that's why
My hmm. um
this is one of
uh,
the reason.
that is one of the reason. And when you are
Okay.
comparing the data sets, ma'am, Brooker is a 400 or 500 megahertz NMR, ma'am.
400, 400.
Yeah.
So
So
they
when
are
you,
comparing our data with the broker 400.
yeah, there is something what
Yeah,
happens is if molecular weight falls somewhere here.
yeah.
So this
Maybe
situation like
this
this,
may be a
when you're
reason.
comparing a data,
Yeah,
you should compare the
yeah,
500 to 500 and you see that. If you're,
yeah.
if 500 you're not getting here, same thing you'll not get in the other instrument also.
Okay, okay.
And my suggestion is, so when you have molecule falls in that area, nosy
Hmm.
is not good, but look at rosy experiment. Rosy is, there is
Okay,
no negative here. It's keep on increasing.
okay, okay,
This molecule rosy is the best one. Like molecular weight from 800 to 2000.
okay.
So rosy is
Roses
the
is
best
best.
one.
Okay, thank you.
Nose is good for the small and high molecules like proteins or like molecular weight above than 2000. NO is bad. Again, please, one thing you should remember that, ma'am, when the molecular size is bigger one, the NOE becomes negative. But in case of representation in the nosy data, it will be positive. Your diagonal and the cross peaks having the same sign. Color will be the same. It won't be different colors for a big size molecule. Sometimes I have
Okay,
seen that some people start complaining that okay, nose, my nose is not giving different colors, giving same colors.
okay,
It's depends on the molecular dynamic also. It's not only it depends on the how you representation, but mainly depends on the molecular dynamic side.
okay,
So this is the major reasons why we are not getting a nose. Nose is very sensitive experiment. It depends on the dissolved oxygen also. If you have a lot of dissolved
okay,
oxygen, if you're
okay,
not purged properly,
okay.
the relaxation goes very fast. So you
So
will
it is a
lose
good.
the nose.
So if we are doing nosy experiment, so we should purge nitrogen in the sample, or matlab-
Yes. Yes, you have
okay,
to purge the nitrogen. It's a
okay,
mandatory. You should purge
okay,
very properly. Then you
okay,
should bring the sample. Huh? And again, the
okay.
temperature must be fixed. When you do a measurement of nosy experiment, fix it for 25 degree or 30 degree, one temperature, constant temperature. So otherwise, what
Okay.
happens?
अच्छा, वन वन थिंग श्रीनिवास जी, यहाँ कुछ लोग नोजी एक्सपेरिमेंट को ना वेरिएबल टेम्परेचर पे भी करते हैं, मतलब जैसे कोई बोलता है कि 30 पे करना है हमारा वीटी
Yes,
नोजी
you can do that.
एक्सपेरिमेंट.
But only thing is,
ओके.
ma'am, when you do the high temp, whatever the temperature is, you have to make it a
हम्म,
stabilized. After achieving a 30 degree or whatever the temperature, you have to wait for
हम्म,
at least 10 to 15 minutes so
ओके,
that the whatever the temperature gradient present in the sample has to goes off. So then only we'll get a proper
ओके,
signal.
बट वी कैन डू नोजी एक्सपेरिमेंट एट हाई टेम्परेचर.
Yes.
ओके, ओके, थैंक यू.
This is the reasons. Next, let me go to the differentiation between the nosy and the rosy. So if you talk about theoretical wise or the experimental side, the magnetization transfer for the nose is a longitudinal plane. As I mentioned, during a mixing time, the whole relaxation process through the longitudinal planes or Z magnetization. But in cases of rosy experiment, everything is works on the spin locking. We are applying the power, spin lock power. So we are locked the magnetization in the transverse plane. And NOE intensity is the best in cases of the nosy because the intensity varies from 0.38 to -1. It's maybe negative, as I mentioned in this previous graph here. So this is a -1 to up to 0.3. You can variations will be there in the cases. But in cases of rosy, you see the bandwidth is very small, 0.4 to 0.8. Only the intensity is very less here. 0.38 to 0.68 differences here. Of course, everything will be positive. You'll hear no worry about any other molecule dependence or field dependent part. Everything will get a good data for the ROSI. But of course, it has some inherent limitations that I will tell you later. So now, as I mentioned, the NOE intensity becomes difficult around the, you can say, correlation area of 1. So this is the one. These areas. Around these areas, the NOE correlation becomes a difficulties. And the region becomes zero. As I mentioned, peptides, when you go to peptide, basically the molecular size falls around 1000 or 1500. So dipeptide, tripeptides, all that. So you will not get NOE. So all the peptide peoples are using only ROSI experiment. You have to do ROSI, not the NOSI. NOSI is not the good experiment for peptides. And the NOSI is good for small molecule, but the buildup rate is very slow because of the T1 relaxation. And intermediate molecules one, you don't get NOE peaks. Just ignore. Don't try NOSI for the medium-sized molecule. Okay. And the large-sized molecule is very good NOSI experiment. And the ROSI is good for medium-sized molecule. Molecular weight between 800 to 2000, you can good. But regarding the low molecular weight or the high size, ROSI is not the good. Mixing time case, in the NOSI case, it depends on the relaxation of the molecule. Small molecule, it goes to 800 milliseconds or maybe a 1 seconds or 2 seconds. Again, depends on T1. And a smaller molecule, so bigger molecule like a proteins or it's a big polymers, the mixing time may be lesser than 300 milliseconds. And the ROSI one, there is a fixed one. You cannot vary too much. It maybe I can say that I mentioned 50 to 200. You can vary from 50 to around 300 milliseconds only, not more than that. Another interesting fact about these two experiments is NOSI exchange protons can give different colors if it is a molecule is a small one. If molecular size is a big, like a protein or a polymer size, molecular weight is a 2000, 3000 bigger size. Your exchangeable protons like a OH, hydroxyl groups, NH groups, these color and your NOSI colors becomes the same. Colors are same. But in case of ROSI, the exchangeable proton gives entire different colors. You can easily distinguish between your diagonal peaks and a cross peak, and your exchangeable proton peaks can be different. Okay. So another fact about these two experiment is artifact part. Okay. NOSI is one of the best experiment because there is no artifact. You will get a very clear signals. Of course, NOSI can give a cozy peak also. The cozy gives the same one contour can have a two different colors. Okay, that is easy to distinguish between the cozy and the NOSI peaks. Okay, cozy peaks in the NOSI experiment looks like one contour will be having a two different colors. NOSI will be having a single contour colors. And the ROSI case, you don't say cozy peaks, but you will get toxic peaks because you see, this is the pulse what we have mentioned here. In the NOSI case, there is no pulse, no artifact. But in toxic case, you are applying spin locking pulse. Because of this pulse is similar like a toxic. If power is little higher side, you may see a toxic peak in the ROSI experiment. Okay, so please remember that while recording ROSI NMR, if you get extra peaks, it may be because of the artifacts. Okay, this is about the brief introduction. I will not go in detail about this experiment. Somebody want to know more detailed about this specific experiment, I recommend you to go to the search. So you will get a plenty of articles. Plus, there are so many videos are available in the YouTube for a theoretical understanding of the experiment and structural characterization part. Now, I'll move on to the one of the example. Anybody has any question now? So till that. Or shall we go continue next step and then finally we can discuss?
Yeah, you can continue, or you can take a break for 2 minutes if you are
Okay, I'm okay.
tired, because continuous 2 hour speaking is very hard, no?
Yes, that's true.
Yeah,
Yeah,
if
I,
you
I
can
will.
take a break of 2 minutes, then you can take it.
Yeah, sure. Okay, okay. Maybe
Yeah,
we'll have a just 2 minutes break. Then we'll just.
yeah, yeah, yeah.
Can I continue, ma'am? Hello. From my side, okay, ma'am. If you're once you're ready, let me know, ma'am. You can just start continuing. Ma'am, okay, so I can continue that. So if
Yeah, you
all,
can continue.
yeah.
Okay.
Okay, now this is I given the brief introduction about the 2D experimental side, and I have taken one example. So just I know you people are chemists, you already using NMR spectrometer and for your assignment purpose. Just want to glance that I have just taken a simple example here. So the example here I have taken is the structural verification side. So there are the two different way to use NMR spectroscopy. The one is the structural elucidation part, where you'll be having unknown molecule. You don't know the structures, then you have to use the NMR spectroscopy. For that, you require different spectroscopy techniques and mass and everything for the structural elucidation side. But second usage will be the structural verification. Now you have synthesized the molecule, you know the rough idea about molecular structure. Now you want to make an assignment of the peaks. Okay. Now in my case, I have taken a molecule with gibberellic acid. This is molecular structure. I have some idea, and this is my formula and molecular weight is here. Now, what I do is in NMR case, the first step is I go to proton NMR spectrum. When I record a proton NMR spectra, I can see like this. I do integration for every peak. Okay. And then I'll start making the counting of that. So if I do that, so normalized and finally I got the number of integration of values will be around 19. But as from the molecular formula, we know that the proton should go 22 proton for this molecule. So the V3 protons are missing. That's maybe it's a very clearly says that you have a OH here, carboxyl group here, and another OH here. 3 protons, there is a chance of exchanging. So we cannot rely on the integration of the particular protons. So that's why those protons are missing out. Okay, you can say one peak at around 11, we are getting a broad hump here. So this may be exchanging with your residual solvent also. Next, I did the experiment of carbon NMR. I got a carbon signal. This. One second, ma'am, just a minute. Yeah, the carbon signal. Just record the carbon NMR. I just counted the number of carbons. So when I did this, you can see the number of carbons will be more here, but there are some carbon signal from the from the solvent also, and plus there are some impurity peaks as well here. Okay. So that is very clear. It's acetone signal of solvent. You can see acetone signal one here, one at here. Now there may be a small peaks at this point. This may be impurities I can consider. So how I conclude that as impurities, because comparing to other intensity of the peak here and this intensity is a drastic difference, large difference. It's very clear that this may be some different molecule. Then I did a depth experiment for all this sample, and then I did depth 135, 90, and then 45. Then the carbons plot. From there, I can make assignment of the peaks, like which is the quaternary carbon. From where I don't get peak, that's called quaternary carbon, and CH2 peak is for this, and CH3 and maybe CH here. So that from the chemical sheet, we can identify the CH3 comes in this area and CH comes in this areas, right? Around 124 aromatic peaks. Then I'll go to the structural characterizations for the 2D experiment. The first experiment which I prefer is to go with the HSQC. So HSQC is a one bond correlation, as I mentioned. So now this is my proton spectra. And of course, please remember that whenever you record HSQC or 2D experiment one, don't forget to load your high resolution spectra on top of here. Okay, this is for the, in case of HSQC, the proton here and the carbon in this side. Now, of course, sometimes problem is like this peak and these contours are not matching. It's a mismatching, you call it. That has to be corrected. That's called referencing point. And maybe I will explain in the demonstration time. Now, see, make assignment. This peak is give a correlation to this. This is called the one. See, this may be the same. This proton and this carbons are coupled. Similar like that. I gave a numbering 1 here. Then carbon we have 2, 3. Maybe now you can see there is a 3 spot. This three protons. 1, 2 here are giving the 2 carbons here. So this may be as this is acetone over here, and this is acetone peaks. We know that this may be impurities. Now these 2 proton may be 2 different protons, but the carbon is the same. So okay, both are giving the same correlation with this. I can similarly make a number of contours assignment. You can see the number of connection part. Now finally there is one thing is as I mentioned, this is acetone peak. It's a impurity. You can ignore that this part correlation. Next, same assignment I continued for my table, which is I created for the depth experiment during that time. So that table I updated with my assignment part, which is numbering I updated over here. Then I proceed for the COSY experiment 1. COSY is basically a proton-proton correlation experiment 1 up to 3 bond 1. So the numbering which is I made for previously, I put on the top of here. Okay. Then I start assignmenting. So now you can see I'm giving the 10A and 10B, 10A and 10B. This is 2 different proton, but carbon is same earlier cases. It gives the correlation over here for B and 4A. It giving 4 here, similar like this. So from this very easy to identify. Now, as I mentioned here, 11 is giving correlation between the 12. This is 11, this is 12. If you do it, this is a cross peak here. So I made assignment like this. 11 give correlation to 12, then 12 is given to the 9, and 9 is given to the 4A and 4B. Similar assignment, you can make that easily. So from this, you can make a verification part of the molecules. Now then I proceed with the toxi. COSY is basically a 3 bond, and if you want a further bond, like in this case, you see this is a differentiate. This is a COSY data. It is a toxi data. Now here, in the COSY case, we are not getting only here, not any cross peaks over in this case. But in the toxic case, you're getting extra 2 contours. It's extended COSY, right? You're getting extra peaks over here. And this is can easily give. Now 4A is giving the cross peak between the 5 here. So this one, it's a long range couplings. It can be seen. So then HMBC is the proton carbon long range couplings. Now I made HSQC data, which is recorded previously, and HMBC data overlapped. Okay. Now wherever the overlap happens, that is called the one bond. HSQC, we know that it's a one bond coupling. HMBC is multiple bond correlation. Now, in case of the HSQC and HSQC HMBC are merging, that is called the one bond. You can ignore that in this case. These are the one bond contours. You can ignore it. Okay. And the remaining all that the HMBC peaks. Now my assignment continued with the same one. So I proceeded the same number to here also. Now 16, 9, 8, 7 connected. 16, 9, 14 is connected. Same assignment can be brought to here also. Now I back to my final assignment table, which is created first and then upgrade with the confirmed from the HMBC one. The number is continued over here. Now these are the Rendic indicates the noise peaks, and these are for the solvent peaks. So other things are the correlation. Finally, I made the assignment for your molecule, my molecule like this. This is the 2D structure of my molecule. Then using the NOSY experiment, this is my NOSY data. So from the NOSY data, I can make the stereochemistry or the 3D structure of the molecule can be obtained from these cases. Okay. And you can see these are the exchangeable proton. As I mentioned, the diagonal peak and the cross peaks having same color. This indicates that these are the exchangeable protons. Okay, it can be seen clearly in the NOSI datasets. Okay, this is about the correlation spectroscopy of routine NMR analysis. Now, another experiment which is interesting for the user, some people are using, that's called a DOSI experiment. Okay, what is DOSI? Is a diffusion order spectroscopy. It's a 2D NMR experiment which provides information about the diffusion coefficient and the chemical shift. So plot looks like this. Indirect dimension, you can see the diffusion coefficient, D values, and direct dimension is the chemical shift values. Now, one of the example, let me go to the what is the applications of this DOSI experiment one. The one application is I can identify the molecular interactions. Example, encapsulations and the molecular capsules can be identified. Okay, the molecular capsules are like nothing but the bigger molecule we have, your encapsulated small molecule inside that. Doing these ones, you know that you are a chemist people. If you guys are knowing that, okay, when you make this one, solubility can be increased and reactivity of the molecule can be increased. So many properties are related to this kind of molecule, host gas complex one. This structure can be identified through DOSI experiment one. So when you have a free molecule, the diffusion coefficient is different. The moment of translation motion of the molecule is different. When you have simple host one, that diffusion is different. When you encapsulate a small molecule into this host one, that molecular diffusion is different. The molecular moment will be different, with even for the smaller molecule and the dimer, this part also. So let me go to the example here. So you can see this is an example. They have taken the benzene encapsulation in the tetrauracils alene dimer. Okay, this is a dimer structure here. Now, when you if you make a free benzene, the diffusion coefficient entirely different, and even the chemical shift. If you look into that, chemical shift values is entirely different. The diffusion is very fast because small molecule, moves very fast. Diffusion is very fast. But when you encapsulate this benzene into the host molecule, it becomes a bigger in size. Now you can see even the chemical shift also got changed. Plus the diffusion coefficient is large, or you can slow movement. And even a free dimer also having a different one. When you encapsulate, it also has a different ones. So from the diffusion coefficient, you can identify the effective molecular radii can be identified, and the association constants can be identified with this experimental sign. It's a very useful experiment science. Okay, and I will not go in detail about this experiment. If someone interested to know about that experiment, I request them to just check it. There are plenty of articles around the DOSI experiment on different application. Plus, there are some YouTube videos just showcasing the how experiment works and where to utilize that. So now what I'll do is, this is about the basic introduction stuff for the today's talk. Now I'll just move on to the demonstration side. So this part, introduction delta software. So I'll just go on to the downloading software and processing 2D NMR. I'll show it in our software sites. Okay, maybe there's so much useful for your research. Minimize this. Okay, so download a software one. You just Google it. You need to type Joule Delta software download. You can see this site, Joule Delta software download. Click. Now you can see there is a Joule LTD site. It shows a Delta NMR software. I just recommend that you can just go to the Joule Delta support site. Go here. Then you have to create your account. If you are a new user, I request you to create a new user account. If you just click it, it'll ask you some few questionnaires. Just sign up with your name and email address and password. So email address, you can use your Gmail ID, or you can use your institute ID also. But when you mention the institute ID, then they'll ask some questions about that, the institute name and other things. But you please mention the full name of your institute. Example, IIT Patna case, you have to mention Indian Institute of Technology, Patna. If you mention IIT Patna's, it won't recognize it. Again, as some errors message comes up. So please mention the full name of the institute. Now let's think you have created account. So to activate the account, it will require at least 24 hours get activations. Okay. Once you sign up, please wait, and you will get an email for the maybe after 12 hours, something like that, saying that the account is activated. After 24 hours, please log in, come back to this same place. Yeah, Joule Delta software, download, go to the site, then just go to the here, log into your existing account. Click. In my case, I have account is already created here. So just sign in with your username and password. Then you can see this page. Here on the top toolbar, you can see software, license key, documents, forums, and FAQs and videos are available. And there are the processing videos are over here. You can just click and you can see there are some tips for the loading samples, license key, different videos are already loaded over here. And plus in the YouTube, there are many videos are available. The forum, which is created for the user, and in case if you get any doubts or questions, you can just post your question over here and you'll get answers at the very faster rate. You can get the answer from here. And if you want to download new software, go to software window here. Then just please accept, mention your operating system. Like in this example, I give Windows and workstation name, Intel PC I have given here. And there are two options for you, data processing or full package. Full packages at the moment is not available for the users who are using for the processing one. So you have to create only a data processing only. Then please mention the Windows version. So I'll just mention, just to showcase, I'll mention 11. Accept terms and condition. Then you can see there is a list of softwares are shown. Now I request to take the first one. Okay, this is Delta 6.3.0. It is the latest released version, processing one. New features are added and that's very useful. I can try it out. Just click on here. It will say that just go to download. Once it download, then it's simple process of download. Double tap that, you can just download it. Okay. After downloading that, it may be a looks. Let me open the software. It says some error message over here. It says your license is valid only for 15 minutes. It is not active. Then you need to activate this for the permanent. Means you have to get the license key. How to get that? Good options on this here. Just find out the license key. Okay, click. Then every PC having the different ID called the mission ID. Note down this mission ID. The current ID which is showing, this is for my PC, but for your PC maybe some random number. That different number will be there. Note that number. Then again go back to your account. Go to the top toolbar, license key. Click. Then again some questions. Accept the terms and condition. Click on the data processing one. PC you need to select. Then here mention all the questions. Then finally they'll ask you the Delta mission ID. Okay, you can just mention the mission ID here. Then submit the button. Once you submit the button, it will show the license key for you in this place itself. So maybe just to showcase, let me give you my ID here. Just to show that license key in this case is mine is here. AP MR and then 61. Then it will be a KJ, then BH. So if I submit this one, then it will show the license key like this. And take this license key, okay, and go back to software again, the same window. Here you have to mention the license key. After that, save key and close and reopen it. After that, you will see the final version of your software. It looks like there's no error message. It looks like this. Okay. So this is how to get the Delta software. And if you find any difficulties, please let me know that. So my email ID is mentioned over here. Please note down my email ID. You can write to me that I can help you out for getting the license key or maybe getting the software sites. Okay. So anyone has a question or I can just move on to the demonstration now. If no question, then I'll just move to the next one for data processing.
Yeah, you can move.
Sign out this. Okay. So now, so let's think you have a software here. Delta, just click one time. I request keep the software in the downside here. Don't keep it in the desktop. When you keep it desktop, here double tapping. If you double tap that opens number of times. Better what you do is you keep the software in the toolbar side. Click here. This one. Now let me show the processing of COSI experiment one. Okay. So now open the data from here, click, and my find out where is your data is located. Now I have open the processed proton NMR. So for a cozy experiment processing one, please take the processed proton experiment. Now in case number 1 is called the unprocessed one. In my case, number 2 is a processed one. How to distinguish that? If it is a processed one, it says in a ppm. If it is unprocessed one, it is in a second. Let me open the processed one. And pin, this is a pin indicates that this window will be active. Click and click, keep it side. Then, so cozy experiment, take the cozy here, and number 2 is selected as ppm. It means processing one. Number 1 is for unprocessed data file. Now click. Okay. So if you unpin this one, after opening the data, this window will be closed. Just see, this is closed. Okay. For a cozy processing one thing is open processed proton spectra and open unprocessed cozy data sets. Now what you have to do is click on this final icon. It indicates that toggling between the spectra and the processing list. Okay. And here you see this is symmetrized function. If symmetrized function is present, select and delete this using this. Click. Okay. Then click on this 2D view. Yes, spectra will open the data view. 2D view. Then please close the backside window. Done. Yeah. Next is loading the, okay, next is the referencing of the 2D spectra referencing. Okay. What is the referencing one? Just to show that, let me give a load X projection, say here. So referencing means now you see, this is my contour here and this is my projection here. This projection is not matching with the contour. There is a shift. Okay. Adjusting this shift to here is called the referencing one. Let me show that. Okay. Now procedure for referencing one. Go to tools, geometry tools, copy ruler reference. Now source A, click on source, click on processed proton. Then target is click target, click 2D spectra. The next X, cozy X means a proton and Y is also proton. So click one time X, click one time Y. Done. Then close the window. Now referencing of cozy is done. Second step is loading high resolution proton spectra on top of both here and here both. Okay. Procedure is go to layout, load 1D, click load X plus Y projection, click and click on spectra. So press loaded. And peak values integrations are not required. You can just hide this. Click here, click Alt and I indicates removing the integration in the keyboard. In a keyboard, hold Alt, press P. The peak values is removed. Now you can see the side Y, the Y scale is not visible. To bring the Y scale, Alt Y, Y scale is brought. And this keyboard command works only with the caps off condition. If cap lock is on, this will not work. Okay, please turn off the caps lock, then try this function. Next step is zoom the contours. How to zoom it? You have to zoom from the diagonal. Start from the diagonal, end with the diagonal. Okay, this is the correct method. Like this is not the correct. Starting from here and zooming this way, this is not the correct. Double tap, full spectra will come. Diagonal, let me put the line for you to understand. Put one line. I click this one in the cursor tool. I click the measurement.
अच्छा श्रीनिवास जी, वन क्वेश्चन हियर. अभी जैसे आपने दिखाया था ना, ये डायगोनली हम इसको करेंगे, आई रिमेम्बर इट। लेकिन अगर ये बीच में से हमने इसको कॉन्टोर को जूम कर दिया तो अंडू कर सकते हैं इसमें?
double tap the mouse, otherwise click on the home button, click on the
Okay. Right.
minus
I remember it. Home. I know.
home
Yeah.
or minus button. This will come back.
Okay.
Yeah. So zooming again, I put the line for you to understand. Just go to zoom and zoom. Start from the diagonal. Stop at the diagonal. Zoomed. Okay. And if you want to remove the line, go to again the measurement. Now blue indicates this line is got selected. In the keyboard, press delete button. That is removed. Next, intensity increasing. Click here. Take in the cursor tool, third option, intensity can be increased. Same thing here, intensity increased here. Second option, move little upside because you have to give a gap between the spectra and the projection. Here also same thing. Then in the this is overview. It's not required. Remove the overview. Layout. Click show overview. Remove it. Again, show 1D ruler. Remove this. 1D ruler means this place. Remove. Now cozy processing is done. How to adjust the contours? Now, if you want to increase the intensity of the contours. Now in Delta 6 onwards, there was a nice interesting tool as introduced. That is just hold a control in the scroll button in the keyboard. Just scroll this up and down. Or you should be in the zoom option. Then hold a control and scroll up and down in the mouse. So that intensity increasing and decreasing. Okay. Done. Then zoom it, and here you can see there are two saving options. Save one is here. If you click this save, it will save with a simple like 2D plot is saved. Maybe let me show you this. So I kept here and click on the save button. It saves number 3 file. Okay. But another save option is called, if you want to save with your projection and the 2D contours together, then you should click this option. This is going to saves in the zip file or the .jda file. Okay, so maybe I can now it's saved both 3 and .jda. Let me show you the difference now. Let me close it. So okay, so where is my data sets? Here. Now you see in cozy number 1 JDA. Now you see this is the one. Now cozy 1.jd file. Okay, it looks in a green in color. If you open that, it opens with your projection together. See, 1D proton projection over here, 1D proton projection here, and 2D contours both are open. It's a saved for permanent. Okay, you can open for 1 month, 2 months later, 1 year later also it will be like this only. It can be opened. And in case of this save option, 1:1 dot, that is the here. Maybe this is a number 3 file. Okay. So number 3 file. So whenever reviewer asks for the raw file to share that, you have to share this one, not the green one. If you share the .jda file, your reviewer cannot open this file. This is only specific to the Delta software. Okay, .jda file. It is just for your reference to visualize.
Here, which one is the best file for data processing? This JDA file or JDF 13 JDF?
JDA file is fine. Once you process done, you can save it as zip file. You can, if you click this one, it comes with the both processing 1D and 2D together. It's like referencing for next year or something like that. And for reviewer purpose, to share the data sets, you have number 3 only.
Number 1, yeah, 3.
Number 1 or number 3 process one you should share.
Yeah.
That will open.
One is raw file, no?
Correct. Now cozy processing is done. Now save, print, click print. And if you want the parameter, go to Delta, take a processing parameter and parameter, black and white in color. Options are available. Print and save it. Desktop and save it. Yeah. Now cozy data is saved. Okay, same. Now this is out of cozy. Now let me show you the another example of, I'll show you HSQC experiment. How to process HSQC NMR. For HSQC also same thing. Open processed proton spectra. Now in this case number 2 file, open and keep it side. And again open processed carbon spectra. In this case here, I have many processes. Maybe I'll take a 6th one. Open here. Next, open unprocessed HSQC spectra. Select here number 1 file has to be process. Select number 1, open this. Okay, yeah. The first thing into the HSQC experiment is put this data into the data viewer window. Okay, click in the data this ND processor window. In this, click on second option here. Click, close the backside window. Okay. The next one is the 2D phase correction. Procedure for 2D phase correction is to layout, 1D view, click on the show X slice. Again, one more time, go to layout, 1D views, put on the show Y slice. Done. The next thing is, so in the context menu bar, or you can say the cursor tool, go to the last second option. This is to select different slides. 2D NMR means this number of slides, right? So you can see this is the one. This number of 1D slides like this. Now you have to select which slides you want to do this. In the context menu bar, go to the second option last. Click here. Select, hold the line on the top toolbar. Now this, please consider only your horizontal line, not the vertical one. Okay. Now horizontal line is touching this red one here. Okay. I'm taking this. When you select this particular one, it shows only spectra for the particular slice. Click a home button, select here, click home button, shows a full spectra. Now here I have taken it. Suppose if I selected somewhere here, it shows another spectra. Spectra for this line here. End key. Okay. Same way. Now phase correction one. Let me put the first one. Selected, peak is here. Click on home. Now put Y scale, please, both the side. Then zoom the base here. Zoom option. See, phase error seen only in the baselines, not in the peak of the spectra. Now here is well phase corrected, actually speaking. Still, I will show that how to do phase correction. Click here. You will phasing options in the cursor tool. Click phasing. The line is appear here. Take the line, keep it on the top of the peak. Now this data is the edited HSQC or depth 135 HSQC. That's why you have two different colors. The CH3 has a different color and CH2 has a different color. Okay. So now maybe let's consider this is my CH3 peak. I want to put in the green and blue color. Red indicates the negative, blue indicates the positive. If you want to tilt or if you want to change that, just keep the line and adjust it. Let me put this is like this positive. Holding left click in the mouse and just dragging that. Okay, adjusted. Then hold right click in the mouse, drag into the middle. This will change. Same thing. So take another. This is called the pi zero, first zero order correction. Now you have to make the first order correction. Click on the last option in the line. Go to the any peak, select from the right side. So from the left side, maybe select the lines from somewhere here. Maybe I will not take a last peaks, maybe in center of that, somewhere here I have taken that. Not exactly center. Now if this is maybe CH3, this may be a CH2. Now the phasing, go to the cursor tool, phase correction options. Don't change the line. Line will be same place. Now hold scroll button in the mouse. Press the scroll button. The cursor will change to pi 1. It's called the first order correction. Adjust the phasing. Now earlier it was like this. Maybe this is phase error. Okay. Make it, if it is negative, make it completely negative. In this case, negative I made. Then right click hold. Right when you right click hold, you can see the finger icon. Then just drag it in the middle. Okay. So done. Now phase correction is done here. Similar things you have to do for the column vertical also. How to do vertical? Go to the selection of these slides. Go to the last option in the context menu bar, like here, this one. Click and take one from the right side.
श्रीनिवास जी, इसमें
Yes,
ये जो पीक है ऊपर y एक्सिस पे, ये डाउनवर्ड है तो ये फेस करेक्ट हो गया?
Yes, this is a depth edited HSQC. So some will be positive, some will negative.
या
So
हाँ, इन डेप्थ में तो यही होता है, some positive and some negative. Okay, I
right.
understand.
So this peak is positive now, and this peak may be negative.
Negative
That's
now.
why.
Okay. Okay.
Let me do the vertical now. Vertical means now you have to consider only a vertical peak, not the horizontal one. So please focus on the vertical line. My vertical line is touching in this line, this peak. Okay. So I'm just considering that. Now you can see peak here. So again, zoom
Can
the
you show
base.
once again vertical line how we will touch to zooming the contour?
Okay. So go to the context menu bar or the cursor tool, go to the last option. And then they click on the middle, you can see the lines, right?
Yeah.
So you have to vertical line has to touch the one of the peak from the right side. Now you can see this line, this is peak is counter stretching. Need not to be a first peak. It may be a starting peaks. You know, if you consider this is my 0%, this is my 100%. Okay, this is my 0, this is 100. Then maybe you can take around roughly around 20% area. Maybe like I can take this peak here. This I can take. Now vertical line is touching, vertical line this one. Okay.
Yeah. Okay.
You can see peak here. Now again, same thing, go to the context menu bar, click first here on the left side, so right side, then go to the phasing option, take the line, keep it on that. Once the line is fixed, then you should not change that. Now the line is fixed here. Adjust that, maybe here. Adjust, done. Pi 0 done. Then hold right click in the mouse. Then the cursor will change into the finger option. Then drag it in the middle. Now pi 0 done on the vertical side. Now you have to do a pi 1 for the remaining peak. Then again go to the line, select here. So now this peak is shown over here. Click pi, then don't change the line. Line is only for the pi 0. You can see pi 0, okay? But pi 1, no changing line. Just hold the scroll button in the mouse, then move up and down. So that's value will change. Then again, you have to apply this number, whatever made a correction has to be applied into the 2D spectra. So hold, right click and drag it in the middle. Now phase correction is done. Okay.
Okay.
After this, please go to the layout, 1D view, on show X projection, go to layout, 1D Y projection. The spectra came. Then next will be the loading. Okay, next will be the referencing of the 2D spectra. Referencing I have mentioned like a cozy, similar way. Tools, geometry tools, copy ruler reference. Now click on source and click on the proton. Click on target and click your 2D NMR. Now please remember your X is a proton, okay? So you have to do only X because Y is your carbon. Now what you'll do, again click on source, click on carbon. Now target, again click on HSQC, then click on Y, because now Y will be referenced with respect to a carbon spectrum. Now referencing is done. The next method is loading high resolution projection. How to load that? Keep side by, process the proton and process carbon in here. Then go to the layout, 2D layout, load 1D, click on load X projection because these two are different. This is a proton, this is a carbon. So you have to make it separately. Load X projection first time, then click on proton. Then click again layout, load 1D, click Y projection, click on the carbon. The projection is loaded here. Now please remove the peak picking and integration. Again, peak picking integration from the spectras. How to remove this? Click here, Alt P, peak value is removed, Alt I, intense integration is removed. So increase intensity, please. So third one, intensity increased. Give the gap between these spectra here. Just lift it up, and here also same thing. Lift this up. Done. The next one is remove this overview. Just go to layout, remove show overview, remove it. Show 1D ruler is removed. So now done is done. Then you can just zoom here. There's no diagonal. You can start zoom from any spot, not the issues. Okay. So zoom. Then intensity decreasing again. Hold control and scroll button. Okay. Adjusting this scroll will become removed. And if you want to make a circle here, there's another option called action smooth option. Click on the smooth. Circle becomes smooth. You know, smoothing and becomes circle. Now you can see example. Maybe go to action one more time, smooth. It becomes circle. But please remember, if you're doing, keep on repeating that, your small intensity peak intensity will reduces. So that's why 1 time, 2 times is okay, not many times. Now HSQC processing done. After that, please save the data and make a print. And then, yeah, take it printing. You can make this print. Desktop, save it. Otherwise, you want to make it a presentation straight away, high resolution if you want that. Now, color is not shown. Maybe if you want to color, go to print, then delta, go to the coloring option here, then print. You can make the color. Okay, this is coloring done. And if you want to make it directly to your presentation file, just zoom this area, then go to file, print to clipboard, click here. Then it'll ask you want which direction, portrait or landscape. Portrait, click, then go to your PowerPoint. So maybe, so you can just paste here. You can take this straight away. Okay. This is kind of high resolution one. If you don't want this parameter one, the first at the beginning only you have to remove this. So I think, yeah, this all you can. While tools, if you don't want that, go to print. Then you please remove these two lines, print, and one time you do the printing. Then maybe you can just again print to clipboard. Then the parameter will not come. Okay, that's all about the cozy processing one. So now I have given the representation experiment for you. So that is cozy and HSQC. Now cozy is a magnitude mode. cozy, HMQC, HMBC, all three experiment processing is a similar way. But HMQC and HSQC, you have to load the heteronuclear correlation spectra. But HSQC, NOSY, ROSY, TOXY, these are the phase sensitive experiment. These experiment, you require a phase correction. So you need to do that. So anyway, phase correction method I have shown in the HSQC, you can follow that. So now what I'll do is I will show you one of the other experiment, which is slightly different from the one that's called DOSY experiment. I'll show the DOSY experiment processing one. Okay. So DOSY experiment processing is the same way. First, you need to open the processed 1D proton spectra. But in the current data, I don't have the proton spectra of the DOSY experiment. I have DOSY data. Once DOSY experiment is completed in your instrument, what you have to do is go to the access the file. Same way, where is that? So go to file, access your DOSY data. So now I have a data set here. Okay, this one, STB PPB LED DOSY. Okay, this is the latest version DOSY experiment. Open this. Now, when you open, number one file will be visible, and you see there's slight different from the normal 2D experiment. In case of normal 2D experiment, like I'll give example HMQC here. Now you see if you take a number one file, it shows S and S. S and S is indicates for the time scale for the both the dimension, T1 dimension, T2 dimension. You can make a Fourier transformation. But in case of diffusion experimental wise, so the direct dimension is S, is a time scale, but indirect dimension is a variation. It's a variation of the gradient strength. That's why it's called a pseudo 2D experimental side. Okay, so it's not the actual 2D, it's basically a pseudo 2D experiment. So the method of processing is a little bit variation from the normal 2D NMR. So let me open this. File can be opened. It looks like this. Now, direct dimension will be having a processing list. Indirect dimension, there is no processing list. You see a difference here. In case of DOSY experiment, direct dimension, you have a lot of point, but indirect dimension, you are getting only 32 point. In case of 2D experiment, like in, let me go with cozy, there's different. You can see there is a 256 point, and here only 2000 point. So this is makes a difference. Now, DOSY is a lesser time, 2D NMR is a larger time. Okay. So 32 is more than enough for the DOSY experiment. Now, processing of DOSY experiment, click here, click 1D, then make the phase correction of the spectrum. Take a phasing, adjust the phase correction first. Phase correction, just adjust the phase correction here, apply, close. Now phase correction done. Next one is you need to see first how data is decaying. So for that, click on the data select. Top toolbar, last third option. Top toolbar in the last third option here. Data select. You can see this is a decay. Direct dimension is simple proton spectra. Indirect dimension is basically a decay of the curve. Okay. So how to see that? Go to the expansion linearize. You can see the decay of the graph. Let me increase intensity. Go to this third option in the cursor tool. Increase this one. Let me lift it up. So here, now you see here, intensity of your signal is decaying. See, this signal is decaying here. This decays happen based on the gradient strength. Now you see this is the gradient strength dimension. This is the intensity scale of your spectra. Now gradient strength is keep on increasing. Spectral intensities keep on decreasing. This is what we required is. Okay. Now let's go Dozy processing one. Click here. Click on the second dimension. Y. Transform. Top transform. Dozy. SPL mode. Then you can just click on the triangle here. Small triangle. Click here. Start button. This is basically a diffusion coefficient dimension, start and stop. Maybe at the beginning, we generally keep the 100 micrometers square per second. Okay. So maybe here in the stop, maybe we can vary from the around 2500 microseconds. Okay. Let me give some idea for you. The start value, you can vary from 0.1 to 200. There is no limit, but just for practical experience, I'm telling you 0.1 micro meter square per second to 100 micrometer square per second. And stop, you can vary from around 800 to 6000. Okay, I'm just first number I taken 2500. Interpolation is just an additional point. You can keep the same one. Species is number of components you are looking for that. How many diffusion coefficient you are looking for that you have to mention that. If you keep it as 0, it's take a automated one. Randomly, whatever the values are that will taken. Then the maxima, please select the maxima. Scaling one, it can vary from 0.1 to 0.5. Okay. As a default, it has taken 0.5. Now I generally use 0.2 or 0.3 in between 0.1 to 0.5. In between, I will take this. What is the impact is the contour size will vary. Let me show you. Maybe I can 0.5. I'll keep it. I'll show you the data for you. Yeah, this is how it looks like. Now let me keep this 0.2 and then just process this. Now you see this is peak is merging here, right? So now here, let me zoom the same area here for you. Now you see how clearly it can visible. Separation is visible. It's not visible. So the reducing a number indicates the contour size is decreasing. Okay. So you can vary from 0.1 to 0.5. So in general, I keep 0.2 or 0.3. Okay. 0.3 is also okay. Now this is how the 2D plot looks like. So direct dimension will become your proton spectra. Y scale indicates for the diffusion coefficient. Now in this example, I have a molecule. The sample is dissolved. This is a TMS peak. Okay. And it has again DMSO, D6, and DMSO water peak. This is solvent diffusion coefficient. Where is here? Solvent is moving here. And is one molecule is moving in the diffusion coefficient and another molecule moving in another diffusion coefficient. And top will be the fast moving molecule and down will be the slow moving molecule here. Okay, and this is done. This is we can see if you want diffusion coefficient
Yeah,
one.
this B counters for solvent.
Yeah, top one is the
Okay.
solvent.
Okay. Okay.
You can process if you want to do. This is one way to do this dosing process. If you keep the line here, it says here Y scale indicates mm square kiloseconds. Generally, this is a little bit complex to calculate that, but maybe I can give in this way. It's basically 0.66912, and the bracket indicates 10 to the power minus 3. Okay, it's again the square here, square, and divided by K indicates 10 to the power 3. Okay, so let me do plus 3. Okay, is a second. This is the meter square. This out. This will go to the -3 and -6. It becomes almost off. The values will be like this: 0.66912 10 to the power -9 meter square per second. This is the value. Okay. So M indicates the milli, K indicates the kilo. Okay. If it is G becomes -12 again. This is how it calculated one. Yeah. This is how to calculate. This is one way to do diffusion coefficient. Now, if you want to make a plot, you can print, and then of course, this is, you can remove this part. You can remove this one. You can remove by layout. Go to layout, go to overview, and remove the 1D layer, and then make a print. Then make the print. Desktop, you can save the buttons. Okay, you can save it. Or if you want a diffusion coefficient measure, this is one way. Okay. Let me give another way of diffusion coefficient. Let me remove this parameter. Press select, delete. Now another way is put this data into curve analysis. Data, click on the data slate, curve analysis tool, go to analysis, curve analysis. Okay, curve analysis. This plot will comes here. Next, you make the peak picking for this. Then select any one of the peak. Now, if you want to know the diffusion, now this is indicates the calculating diffusion coefficient for the individual peak. Let me go to this peak now. This one. Now I can, this is my graph for the particular peak. Or if you want to make everything one, select all of the peaks. Okay, maybe you can ignore this, maybe not the right one. I think this, let me put the threshold because peak picking is not the correct one. So now if you take this one, this is my graph. Now if you want everything one, select all of the peak. Then on the side by right side top, you can see that mode. You select the diffusion here, downside diffusion analysis. Then apply. So you can see these values here. Okay, 7 point. This D indicate diffusion coefficient. Now, if you want to generate a report from this, you click it here. So this is a top toolbar, create a report for the fit. Click. Then it will ask what are the points you want to include. You can include the standard deviation if you want. You can include standard deviation and number of points and all these slides, and then the create file. Report created. So this will be saved. This report will be saved along with your data files. If you want to access here, click here. Then it will open your delta first window. If you've seen that, so delta first here, if you click on the IE, so this window, say this window and that window both are same. Let me click here. This is data analysis one. You can see individual plot. So now this is the gradient strength, this intensity variation of a peak, and finally calculated here. D will be calculated over here. You can see D values given for individual peak. So this can be exported. Maybe if you want to make a PDF, you can make the PDF. Otherwise, if you want to make a text file, go to the report, save text file, go to desktop and save the file. This file is saved, and that data can be plotted in your Excel or Origins, anywhere you want to see. You can plot that. So here it's the data sets here. You can see. Now, if you put this one graph, this is your X scale, this is a Y scale. The same graph will appear in your Excel sheet or your Origin or even anything. Then you can make the calculate your own way for the effective radii of this sample molecule can be calculated from the fitting. So this is how to calculate. I think I'll just wind up at the moment. So anybody have a specific question, want to see some specific processing, let me know that I can show you this. Thank you so much.
Okay. Dr. Srinivas, thank you for a very nice presentation.
Thank you, ma'am.
Okay, participant can ask the question. Shamim, you have any question?
Sir?
Yes, yeah.
I'm asking from Shamim.
Sir, from if the sample is polymer, then can we check the NOSI at 20 degree?
Yeah, you can do that. polymer, that depends on how it behaves. If polymer becomes a gel or solidiforms, then it's difficult to do the nosy experiment.
No, sir,
You
it
know,
is solid in D2.
see, the polymer, again, problem nosy is that you have a fast rotation, correct? You have a simple linear chain. When the polymer having simple linear chain, the bond rotation is fast. When the bond rotation is fast, the nosy is not effectively seen for the neighboring protons. But anyway, if restricted motions or if it is fixed geometry, then nosy can be seen. Plus, practical problems. If polymer is completely a gel, I mean, it's completely solid, liquidified, no issue with the 20 degree, you can do that. For instrumental side, you can run. Water means you can run till 5 degree or 8 degree, you can do the experiment. No issue.
Okay, sir. Okay, sir. Thank you.
Sapna, I think you are asking some experiment about experiment. Some.
Yeah, waterlogsy can be done in your system. Yeah, that pulse sequence is already there. So maybe let me try to open my virtual machine. If it works, they can show you this. My PC is not working. See, waterlogsy, once you collected the data, generally there are two types of experimental waterlogs. You can filter out your protein signals, and once the experiment completed, automatically this signal variation gives. Okay. The binded one gives negative, not binded gives a positive, that automatically signal comes. You need not to do any kind of phase corrections. So you can just plot and compare with the proton spectra, which is recorded. So that will give indications. There is no extra processing is required. Only line broadening factor you can use around 2 Hertz SXP value. So line broadening factor is nothing but, so in experiment, you can see there is one parameter called SXP. Suppose if you are using mesitrinova, there is called apodization function. So line broadening factor. Okay, you can use this value, you can use it for a 2 Hertz for waterlogsy. This experiment is already there in your system. You can do that. Whenever you want to do a waterlogsy one, let me know that. Maybe I can come to online. I can help you out setting up the experiment. I hope I answered the question.
If she will ask this experiment, okay, so we will call you online.
Yeah, that's better. Yeah, I can.
Because I think previously we have not done that kind of experiment.
Correct. Waterlogsy is not done, and yesterday type experiment, waterlogsy, anything if you want, let me know that, ma'am.
Yeah. Okay, any other question from the participant side? Okay, can we close the session? I think participants have no questions. Okay, Dr. Srinivas, actually I got many idea from you earlier and today also. Okay.
Hello.
Yeah, I thought Shamim. Okay, you can ask.
सर पूछना है कि नोजी एक्सपेरिमेंट में स्क्रीन ऑफ क्यों हो जाता है?
नहीं वो बोले हैं ना कि सारे 2D एक्सपेरिमेंट में स्पिन ऑफ रहता है आइडियली.
यस
हाँ, प्रीवियसली उन्होंने शुरू में बोला था ना कि 2D एक्सपेरिमेंट में स्पिन ऑफ रहता है.
And especially for nosy experiments, spin off is a must. And if you do COSY, HMQC, I think I have not kept spin-off for COSY and HMQC. That is okay. That is no problem. It won't make any much difference. But NOSY experiment, you have to spin off that.
Acha, Srinivas, one more question here. Whenever we have time, so we will ask you about the nosy experiment, and I think you should reduce the time, because here it's taking 4-5 hours. So I think this
Now, I
is much
think
time.
Joydeep was talking about you have some issues with solid state experiment. It seems.
Yeah,
Maybe
yeah,
I will plan a visit once over there. So
I am asking also about that.
yeah, so I think he already told me 2 times, so I
Yeah,
was not
but
getting the
I
time.
think this time please spend one week, okay? Because
Will come for
solid.
solid state and solution, both will do
Yeah,
that.
yeah. Because our operator has been changed and new operator is Ataf Shamim.
Okay.
And I also. So please come
Yes,
and
I'll
decide the
update you,
visit
ma'am,
as soon
once.
as possible. Yeah.
Yeah, I will just, once plan is finalized, then I'll just let you know, ma'am.
Okay.
We will do solid state first priority basis. Then,
Yeah.
meantime, you
I
can do
think
solution state also.
solid state as well as dozy experiment and little bit
Okay,
nosy. Okay,
no
only
issue,
three
no issues,
experiment. Yeah.
no issues, ma'am.
Okay.
Sure.
Okay. Any other question from participant side? Okay. Dr. Srinivas, thanks a lot. Okay,
Thank you very
for a
much,
nice
ma'am.
presentation. I think we can
Thank you.
close the session.
Yeah,
Yeah.
sure,
Yeah.
ma'am, sure. Thank
Okay.
you so
Thanks
much
a
for
lot.
arranging all
Yeah.
this. Yeah,
Yeah. Okay. Thank you.
just leaving the meeting now.
Yeah. Okay.